Alright, so first of all, we need to confirm that these triangles are similar. If they are similar, then we can use proportions to solve for our missing side lengths. So we've got parallel lines. I know that corresponding angles are congruent. When I have parallel lines, I could mark the other ones as well. But I also have this shared angle right here. Alright, so they're similar by angle. And actually, once we prove them similar, we're done with the parallel lines. We're not really going to use that at all in this problem again. We'll use it later in the lesson. Okay, now what I recommend you do when you're finding multiple side lengths like this is I recommend you draw them separately until you get used to these types of problems. Because here's what you are not allowed to do. Watch the wrong way really quick. Ready? This is wrong. This is bad. 15 is to 6 as 10 is to y. 15 is to 6 as 10 is to y. Bad. Don't do it. That's how people get the wrong answer. Okay? Those are not proportional to each other. And we'll see why when we draw the triangles separately. So if I drew them separately, I've got my small one and then my larger one. 12, 15, 10. They gave us all the dimensions of that smaller one. Now let's do the larger one. What's this side? X. What's this side? Y. And be careful, what's this side? Oh, you have to add them together. You can't just use 6. 6 is not a side, it's a partial side, right? Okay, now we can set up proportions. You find two sides that are corresponding, and those I call them the key to your proportions because you can keep using that ratio over and over again. I don't even reduce it most of the time. 21 is to 15 as x is 12, and then use it again. 21 is to 15 as y is to 10. And then you get your calculator out and you do a whole lot of cross multiplying. 21 times 12 divided by 15. What's x? Yes, 16.8. Alright, x is 16.8. You will notice, and the rest of our time in geometry, we will have answers that are not always whole numbers. Yes. And y cross multiply, and you get 4. So notice, on this triangle, we needed to draw them separately and set up a nice proportion. That way we didn't make any mistakes with using like a partial side. Okay, now we're going to learn a theorem that's going to let us use partial sides. But we can only use partial sides sometimes. So let's write down the theorem first. Okay, write down Triangle Proportionality Theorem. That's the title of your notes. Triangle Proportionality Theorem. And here we go. There's the theorem. Might be hard to see. If a line parallel to a side of a triangle intersects the other two sides, then it divides the sides proportionally. So we're saying pretty much if we sum up the theorem, we're saying if parallel, then proportional parts. Because I'm not even going to call them sides. So if those lines are parallel, then it splits the sides into proportional parts. So this is saying if EF is parallel to BC, if they're parallel, then part 1 is to part 2 as part 3 is to part 4. 1 is to 2 as 3 is to 4. Do you see how we're using partial sides there? That's this new theorem. It's like a shortcut. It's like, oh, sometimes you don't have to draw the triangles separate and do all of that work. Sometimes you can just say 1 is to 2 as 3 is to 4. What it does not work with, be careful. Notice in this proportion right here, it does not mention EF and it does not mention BC. It does not work with those segments. It only works with 1 is to 2 as 3 is to 4 in my picture. So when you have a problem that's asking for BC or asking for EF, you are not going to use this theorem. This theorem does not apply to that problem. You do it like we already did earlier in the lesson. I already showed you one of those. So let's look at these different situations here. Compare and contrast these. So it's kind of like when does the triangle proportionality theorem apply and when does it not apply? So remember it says if they're parallel, the sides get split proportionally. So 6 is to 5 as 5 is to 7. Whoa, that is totally false, which means that these are not parallel. What about here? 2 is to 4 as 5 is to 10. Well, that is a true statement. So these are parallel. 3 is to 9 as 5 is to 15. Well, 3 times 3 is 9, 5 times 3 is 15. So these are parallel. Last one. 2 is to 6. Sorry, as 4 is to 1. Well, that's not even close. No way. So those would not be parallel. That's a parallel sign slash through. So anyways, it's saying if we're splitting them parallel, I'm not saying it's a midpoint. This is not a mid-segment, even though a mid-segment is parallel to the third side. If they're parallel, the sides that are created, the segments are proportional. That would be the converse of it. So the theorem says if they're parallel, then the sides are proportional. The converse is if the sides are proportional, then we have parallel lines. Yep, converse and the original are both true. Let's do some examples. Find the length of EC. So I'm just going to dive right into this, not really give you time to draw it, but it's because it's so simple. So we're trying to find EC. You do not have to draw the triangles separately and go through all that work. Because we have parallel lines, we can say 32 is to 24 as 40 is to x. It's just a nice little shortcut. Could we have solved this one without that shortcut? Yes, but it saves us time, which is always important. Okay, not even going to solve it. You know how to cross multiply. Next one, find Rn. So, yes, confirm that they're parallel. Now, 8 is to 5 as 10 is to x. So it's like this one is to this one as this one is to this one. They're the parts created by cutting through with that parallel line is what you're comparing. All right, that one's just like the other ones. Let's do one that's a little bit different. Let's do this one. Find the length of XZ. So if we wanted to use our new theorem, we can't use 30 and 18. We would need to subtract them. We have to use the parts, the segments that are created. So I'm going to write 12 here. Okay, now we've used U, so don't use it again. We're trying to find XZ. So there we go. If we wanted to use this theorem, it would be 12 is to 18 as x is to 30. Same thing here. Same thing here. Subtract these first, and then you can set up your proportion to find that one. We had a lot of examples. Okay, let's do this real world one. On the map, 1st Street and 2nd Street are parallel. Okay, let's go mark that on our map. You are parallel. What is the distance from City Hall to 2nd Street along Cedar Road? So from City Hall to 2nd Street along Cedar Road. Okay. If we want to use our new theorem, we can't find x right away. We're going to first, when we set up our proportion, we're really going to be finding, I'll call it y. Then, once we know y, we can add it to 2.4 and get there. Okay, so I can now set up my proportion because these are parallel. So 2.1 is to 2.8 as y is to 2.4. So I said square is to square as underline is to underline. Cross multiply those. Okay, so good. Y is 1.8. And now we add it back to 2.4 so that we can find the distance from Cedar Hall to 2nd Street along Cedar Road. 4.2. What do we have? Okay. this is the last type of problem that I can give you. Verify that MN is parallel to KL. So this is just when we're using the converse of the triangle proportionality theorem. If those parts are proportional, then those segments are parallel. So let's do what we've been doing the whole time. 42 is to 21 as 30 is to 15. It's either true or false. If it's true, then the lines are parallel. If it's false, then MN is not parallel to KL. Yes, those both reduce to 1/2, or to 2 actually, both times. So they are, and that's you right there. That is you verifying. You can even reduce it. 2 equals 2. So I have verified that MN is parallel to KL. Since, and I could write it out like this if I needed to, or it might be multiple choice on a test. Since MJ divided by KM equals NJ over LN. Since this is true, we have our parallel segments. Does the triangle proportionality theorem apply to PQR? Justify your answer. Ooh, this is a good one. So how would we decide if we could use it here? So Alex is saying we need to figure out if they're parallel. How do you know if they're parallel? Yeah, we learned, like the 3rd week of school, that parallel lines have same slope. So if we can find their slopes, if their slopes are the same, then we're allowed to use the triangle proportionality theorem. Oh, and all of last year. I know you didn't learn it in geometry. Okay, so let's count their slopes. Rise over run. 1, 2, 3. 1, 2, 3, 4, 5, 6. There's the slope of PQ, MN. 1, 2, 1, 2, 3, 4. So 3 over 6, 2 over 4. Their slopes are equal. Therefore, we could use the triangle proportionality theorem. Because remember, in that theorem, the hypothesis is if they're parallel, then the pieces are proportional. And so we fulfilled the hypothesis, so we could use it. Alrighty, guys, that's all.